Let's talk about rules of inference. If you're taking a philosophical logic course, this is your primary method of proofs. You don't do logic laws, you don't do truth tables, you just do rules of inference. And rules of inference are used for taking a set of premises and getting to a conclusion, kind of like a logical argument. So the first example I have is, if it rains, I will get wet. It's raining, therefore, these three dots mean therefore, I will get wet. And this is a logical argument. I'm saying, look, if R, then W, R is happening, therefore W. So this is a logical argument, and this is what rules of inference are meant for. So we take usually one or two premises, and we can deduce a conclusion from them. So these are premises, and this is a conclusion. So R arrow W, R, therefore W. And there's a bunch of different rules of inferences, but more generally, we say that a set of premises, P1, P2, all the way up to Pn, prove some conclusion Q in an argument. So this is about arguments. And an argument is valid if the premises logically entail the conclusion. So if all of our rules of inference take us from the premises to the conclusion, then it's valid. If there are improper steps, or steps that aren't logically equivalent in there, then it's invalid. So saying P1, P2, all the way to Pn prove Q is the same thing as saying P1 and P2 and all the way up to Pn arrow Q. So in the previous example, R arrow W, R therefore W, this is the same thing as R arrow W and R arrow W. And with a truth table, this would be a tautology. So all of our rules of inferences of this form are going to form tautologies. So with that in mind, let's take a look at rules of inferences. So first one is modus ponens, and this is sometimes referred to as affirming the antecedent. So if I have P arrow Q and I have P, then I have Q. This is like sticking the thing into the arrow and getting an output. So if we have P arrow Q, then this says, oh, if we have P, then we have Q. Well, we have P, therefore we have Q. Modus ponens, this is normally shortened as MPP. MPP because this is actually modus ponendo ponens, but we just take the ponendo out because, you know, we're discrete math people, we're not philosophers. 2, modus tollens. Well, modus tollens is the opposite way. So this is sometimes known as denying the consequent. So if we have P arrow Q and not Q, then we get not P. And if you remember, P arrow Q is logically equivalent to not Q arrow not P. So this is kind of like doing modus ponens on the contrapositive. You can think of it like that. So if you wanted, you could just do the contrapositive law and then use modus ponens on that. That's another way of doing things. And this is sometimes shortened as MTT for modus tenendo tollens. Yeah, there's a lot of tenendos and ponendos that we just remove, but MTT is the typical abbreviation, so we'll keep it like that. Okay, third law, hypothetical syllogism. It's kind of like transitivity. So if we have P arrow Q and Q arrow R, then we can just say, oh, it's P arrow R. We're kind of like taking out the middleman. We're saying, oh, if we have P and we have Q and we have R and we have these arrows in between, let's just take a shortcut and go straight from P to R. So that's what the hypothetical syllogism is, and that's typically abbreviated as HS. That's just taking a shortcut. Kind of like taking these Q's and merging them together and then just forgetting about them. This one isn't typically used too often, and usually we can get around this just by doing two operations of modus ponens. So if we have P in here, we could just do P arrow Q giving us Q, then Q arrow R giving us R. Or we could shorten it by doing P and P arrow R, then get R out of it. Either way works. So hypothetical syllogism isn't a required step normally. Fourth, disjunctive syllogism. If we have P or Q and not P, well, if P or Q is true, that means one of those has to be true. But we're saying not P. Therefore, it has to be the case that Q is true. And this is again abbreviated DS. So again, P or Q. This says P is true or Q is true. But this not P says that P is false. Therefore, it has to be the case that Q is true. That's what disjunctive syllogism is telling us. Okay. 5. Addition. Addition is really straightforward. If P is true, then P or Q is true. And sometimes this is just known as OR introduction for VI. So OR introduction. The I is for introduction. And this just states if P is true, well then P or anything is going to be true. That's just the definition of the OR. Simplification, P and Q. Well, if P and Q is true, then P is true and Q is true. Therefore, P and therefore Q. Sometimes this is also known as AND elimination because you're removing the AND from it. So simplification is pretty important. The opposite of simplification is conjunction, also known sometimes as AND introduction. So if we have P and we have Q, and those are both true, then of course P and Q is going to be true. So simplification is removing the AND, conjunction is adding the AND in between two true statements. Okay. Those are all the rules of inference that we need to do some proofs. And of course, if you remember them all just seeing them out the first time, wow, incredible. Of course, I expect you to pause the video and go back and learn them and do practice with those. But let's just do some examples. So for the first one, I have 3 premises. I have R, R arrow D, and D arrow not J. And I want to prove that 1 through 3 entail not J. And we need to justify every step. So the first thing I always want to do is I always want to do modus ponens. It's like the first thing, if I see something and I see something arrow something else, I want to stick them together. So the first one, I have R and R arrow D. So I can do modus ponens on those, and I can get D. And to write a step in a proof, we want to say, okay, so using line 1 and line 2, we did modus ponens to get 4. So from 1 and 2, we did modus ponens. So R and R arrow D gives us D. 5. Now I have a D, and on line 3 I have D arrow not J. So through modus ponens, I can get not J using 3, 4, and modus ponens. So we have shown, using our 3 premises, that we can get not J. Now, of course, that wasn't the only way to do things. We could have used hypothetical syllogism. So using 2 and 3, we could have merged R arrow D and D arrow J together to get R arrow not J using hypothetical syllogism. And then we could have applied modus ponens on lines 1 and 4. So 2 different ways to do the same proof, or to get the same conclusion. Let's do one more example. So I have not R or not F arrow S and L. I have S arrow T and not T. And I want to show that R. And right away you're saying, whoa, this isn't just modus ponens, what's going on? Yeah, it's not always super straightforward. But what do we see? Well, we see not T, and we see S arrow T. So I think this is a good time to use modus tollens. So if we have S arrow T and not T, this means we get not S. So this is 2, 3, and MTT. So now we have not S, and we're thinking, what can we ever do with this? Well, in line 1, what we could do is we could just use the conditional law and see where that gets us. Or we could take maybe the contrapositive of 1. So again, we can still use our logic laws if we want. That's still available for us. So the logic laws with the contrapositive, we would get not S and L, arrow, not R, or not F. Okay, and this is just line 1, and this is just the contrapositive. Okay, so now we're a little bit closer. So let's use another logic law that we have. Let's use De Morgan's law on both sides of these. So we'll have not S or not L from using De Morgan's on the antecedent. And then De Morgan's on the consequent will give us not R and not F. So that's on 5, and that's using De Morgan's. Okay, 7. Well, let's use double negation just to make things look a little bit nicer on the right side here. So that'll be R and F. And that's 6, double negation. Okay, finally we have something we can work with. So we have not S, and we have not S or not L, arrow R and F. Now using addition, we can get not S or not L, and that's 4 and addition, or otherwise known as or introduction. Now finally, we can do modus ponens with 7 and 8 to get R and F. Now why can we do that? Because we have not S or not L, and 7 says, well, if not S or not L, then we get R and F. Therefore, we can do modus ponens to get R and F. And finally, using simplification, we can pull out R from the conjunction. So that's 9, and that's simplification. So there you go. There is a much more complicated proof of rules of inference, also using some of the logic laws. So rules of inference is really like the capstone, the peak of propositional logic. It is usually incredibly difficult at first, and then once you get more practice, it gets much easier. But of course, in a philosophical logic course, you don't have the logic laws to work with, and you also have a few more rules that I don't introduce here, because in discrete math, you normally don't introduce things like reductio ad absurdum or other things. But if you have any questions about this, of course, feel free to ask, and I will do my best to respond.